is section 1.3. We'll start out looking at correlation coefficients. The correlation coefficient, which we label as R, the letter R, is a measure of how well the data points form a straight line. Now, the measure is always going to fall somewhere between -1 and +1. And -1 is a perfectly straight line that's pointing downwards, has a negative slope. And +1 is a perfectly straight line with a positive slope. And 0 means that it's either a flat line or the points are scattered. There's no correlation. So let's look at the graphs here and see if we can match up these numbers in the box to each graph. So we have some that have fairly good correlation. They're fairly straight lines. I'd say these two are probably the straightest. Then we have a couple more, probably these two here, that are okay, not great. We have a flat line that's very straight, and we have kind of complete chaos going on here. So the two straightest ones are going to be our 0.9 and our -0.9. They're pretty close to 1. Since this one here has a negative slope, since the slope is down, we're going to make this one the -0.9 and this one down in the bottom right the +0.9. The 0.7s that we are choosing from here have pretty good correlation. They're pretty straight. The negative one here has a trend downwards, and the one over here has a trend upwards, so that's going to be our +0.7. And then finally, even though this one has a perfectly straight line, it's a flat line, so that gives it a correlation of 0. It means that one variable does not affect the other. And same thing here, one variable, again, does not affect the other, except this time the results are a little bit more chaotic. So both of those have a correlation coefficient, which we call R, of 0. Now, percent explained is when we take that correlation coefficient and we square it. So when we do that, we convert it to a percent, and that will tell us how much the x variable explains the change in the y, explains the variation in the y. So let's take a look at this. This line before we said had an R value of -0.9. So let's go ahead and square that. So if we square -0.9, we're going to get a +0.81. If we convert that to a percent, that's 81%. So that means that our x variable explains 81% of the change in y. And you can see that some of the variation in y isn't perfectly predictable from a straight line, but most of it is. In fact, 81% of it is. Same idea over here. We have r equal to 0.7, so we square it, and then we get an r squared value of 0.49. So that means 49% of the change in y can be explained or predicted by the value of x. So that's why when you look at correlation, 0.7 is kind of a magic tipping point where more than half or less than half explained, because 0.7 squared is just under 50%. Now let's go ahead and actually put a trend line on these data. So we call that a least squares regression line, or sometimes just a regression line, also known as a best fit line. So there's many names for this, but it's just a straight line that best matches the data. So in this case here, if we had to put a straight line in here that best matches the data, it's going to be something pretty close to that. Now if you do it on your calculator, which I'll show you how to do in a moment, you can get that exactly fit. But usually, just using your eyes, you can come up with a pretty good guess and get pretty close. Same thing over here. Let's go ahead and see if we can find a good line for these data points. Now, it doesn't necessarily mean that exactly half of the data points are going to be above the line and half are going to be below, because points that are really far away, like this little one here, actually have a larger effect. So there might be more points up top, and the points below might be a little bit farther away. So maybe scoot it up a little bit. But your calculator, what it's doing is it's figuring out how far are these away, how far are these points away from the line, and then it squares each of those values and tries to make that as small as possible. Now doing that by hand is something you couldn't do, but that's why we can just make a quick visual estimate for this. Now we're going to get into the details about the distance away. That's actually called a residual. A residual is the error in the best fit line prediction of y. So you take the actual y value. So let's go ahead and pick a point here. Let's use this one here and say, okay, this is the actual y value, but given this x, whatever x this is, our best fit line predicted that we're going to have a point around here. So the distance from here to there is the residual. We take the actual point minus the predicted point, the actual y value minus predicted y value, and that's what our residual is. So if we do that for all of these, we're going to get something close to this. These little purple lines here are the residuals. They're all of the error distances. So this point is this far away, this point is very close, this point down here is a little bit away. Now sometimes you're asked to create a residual plot. That's where you take all these residuals, all the distances away from the best fit line, and you plot it as positive and negative numbers. So your x values stay the same. If you, for example, had x equal to 5 right here, this point right here would also be x equal to 5. But now your y value is the error. It's how far away, how long these purple lines are. That's what your y values will be in this example. And this is called a residual plot. It is just a quick little graph of all the residuals. The reason this is useful is it helps you see how much error there is and how predictable of a pattern it forms. Sometimes if it's chaotic like this, you know that you probably have a pretty good linear fit with your line. But if all of them were below, then you would know something's wrong. So now we're going to look at a little bit of a silly example here to help you understand the concept, and we're going to do it in your calculators. So we have an x variable, which is the number of puppies, and our y value is the number of happy children. And what the logic is for this one is that the number of puppies will explain how many happy children there will be. And we assume a positive relationship, so more puppies means more happy children. But we want to figure out exactly if we can predict how many happy children we'll get from any given number of puppies. To do this on your calculator, you need to pull up your main screen here and click on the Stat key. And then right away, the first option, hit Enter to go to Edit. So Stat Edit. And what that's going to do is that's going to bring up some lists. So once you're in L1, you want to make sure that this is empty, and then you start typing in your x values. So I'll go ahead and clear this and just do this as a quick example. The way you clear it is you hover over the L1, hit the Clear key, and hit Enter, and that'll clear a list for you. So 3, Enter, 8, 9, 12, 14, and 17. And you do the same thing for all your y values. You put that under L2. Once you have this in your calculator, we're going to go ahead and make a scatter plot. So first thing you want to do is check that your scatter plots are turned on in your calculator. So go to second, y equals, which will be your stat plot. Now mine happens to be turned on, but I'm going to go to plot 1. And right here, it'll give you an on or off option. So if yours is off, put it to on and hit Enter. And under your type, you'll want this first one. This first one is the scatter plot option. And after that, you should be good to go. You'll also want to make sure that your y equals is cleared. So I'm going to go ahead and clear anything in my y equals. Then I'm going to go to Zoom. I'm going to go down to the 9th option, Zoom Stat. So you can either scroll all the way down, or you can just push the number 9 if you forget. So Zoom Stat. And then I'm left with this graph. This is my scatter plot. The next thing I'm going to do in this example is figure out what our best fit line is, or our least squares regression line. So to pull that up, I'm going to go back to the Stat key again, and go over to Calc this time, and go to the 4th option down, LinReg, which stands for linear regression. So once this comes up, it'll show up on my home screen. I'll just push enter, and it'll come up with four variables: a, b, r squared, and r. Now, if you remember, r is our correlation coefficient, so this is how good the fit is, how straight of a line it is. So 0.95 is pretty good. Anything over 0.9 is usually pretty good. R squared of 0.91 means that 91% of the number of puppies explains 91% of the variation in the number of happy children. So it doesn't explain 100% of it because there's a little bit of wiggliness in the data, but for the most part, the number of puppies explains 91% of the variation in happy children. So we have this information here. Now if we want to go ahead and plot a line on our graph, let's do that. I'm going to go to my y equals, and we need to type in the equation of the linear regression line. So it's going to be y equals, and this a term here is going to be our slope. So 0.912 roughly times x. So 0.912x is what I'm going to round it off to, plus my y-intercept, so plus b. And you can just follow the pattern right on the screen there. And b is 4.247, we'll say. .247, and then we just go back to graph, and it'll plot the line right there for us. And so I've got that under here. So we've got our y equals that we typed it in here, and then you graph your line on your scatter plot. So let's review what we just found. So we have our correlation coefficient, which was r here, 0.956, and that's a very good fit. Then we have r squared, that's our percent explained. And if you convert that to a percent from 0.91, it's 91.5%. So the number of puppies explains 91.5% of the variation in the number of happy children. Next, our least squares regression line, we looked at this pattern here, and we said it was y equals 0.912x plus 4.247, and then we plugged that into our y equals. I rounded here, but that's the basic idea. If we look at our slope, it was 0.92. That was our a term. And if we want to contextualize that and see what it actually means in words, it's the number of happy children that we get for every puppy that we add. And if you kind of look at this, the number of happy children seems to increase at a rate close to 1 for every puppy we add, but it's a little bit less. But we have a y-intercept. We didn't start at 0. So our y-intercept is 4.247. And what that means is that's the number of happy children we had when there were no puppies at all, which means x equals 0. So just like in a normal line, if you plug in x equals 0, your y-intercept is the b term on the outside. Same thing here, 4.247. And since our y term is the number of happy children, that's also going to be, our y-intercept is going to be a number of happy children. And that is correlation with regression.